I'm excited to be here because I looked at the class syllabus and it looks really good. So it's super relevant. So my name's Hayk. I work at Skydio. I lead the autonomy team there. Skydio is a startup in Redwood City that makes vision-based, fully autonomous drones. This is the drone we just launched, the Skydio 2, and it does a lot of the stuff that you've been learning in this class. And so I mostly just want to show a bunch of visualizations, talk about the way we think about things, and please ask lots of questions because that's the whole point. So I'll just pass this around if you guys want to take a look. There we go. I don't think I'm allowed to fly in here, but I would. And you'll have to excuse my mustache, but it is November, so. Okay, so just to get you guys interested, I'm going to show the first, 40 seconds of our launch video for this guy, which we launched just, a month ago, and we're shipping out right about now. So, go. All right, so you can watch the rest. It's pretty good. But I'm just going to talk very quickly about the point of our company and then just jump into technical stuff. So basically, drones are really useful because you can have an eye in the air moving around in 3D, and that's useful for just a ton of different industries. And this is nothing new. The problem is that I think the technology for them to be safe and trustworthy and intelligent in the wild in enough places hasn't been there. And so that's the point of Skydio. From day one, it's like, let's make the technology for this type of robot work such that it can go out and do things in the world. So basically, we've been invested in this, like building the whole stack. And the reason we build the hardware is because the whole thing just matters. Like you care a ton about weight and size and power and cost, but also just about the quality of the cameras, the exact vibration characteristics of the thing, the electronics in play, the power system, the embedded system, and the software on top that runs. Controlling the whole thing makes it possible to push the limits of robots, and that's why we do it. And so not just this is the consumer launch. That video is regarding this awesome video capture for anyone without needing to be an expert pilot, but it also makes a ton of sense for any task where you're inspecting things like bridges and cell towers and pipelines and rooftops, anywhere that's dangerous, anywhere that's costly, and you need to build a map of things. So for construction, for mining, it's a long list. So as long as you have something that is trustworthy, intelligent, can automate tasks, and get even just video data, it's incredibly useful. So that's our goal. This is another slide that says the same thing. Okay, and then here's just a view of kind of the more commercial side of this. So the idea of being able to get up inside kind of these high voltage trusses and power lines and take close inspection photos. This is something that's very hard to do manually, and it's dangerous, and these things need to get inspected all the time, and it's incredibly expensive. And then on the right is us being inside kind of just this narrow bridge truss with metal on all three sides. So something you really can't do with GPS. It's not possible. Cool. And then finally, I'll show this product that we just kind of announced that we're super, super excited about, which is called the dock, also commonly referred to as the box, which is essentially just a cozy home for the drone. that is weatherproof, and basically it pops out, the drone flies, it does a task, comes back and lands and goes in. And the thing's cloud connected, and the whole idea is like you have this robot out somewhere on your construction site along a pipeline, and the drones go out and do tasks on a regular schedule, and then they come back. And the whole thing is hands off, and it's truly like just an autonomous thing that's doing work. And so it becomes more of a cloud platform where people can use that rather than, you know, someone is piloting this robot and in control of it. And that's how we see the long-term play of this going. Cool. So here's a video that just shows, it's just a clip of a mountain biker that we think is a pretty good shot of just autonomous visual tracking following. So the drone is doing all this computation, of course, on board in real time, based on visual tracking. And we're able to kind of get some nice cinematic video here with tree occlusions, with fast motion. And here we're getting a shot from the front, which we call lead mode, which is pretty tough because it means you have to do a lot better job of anticipating someone's motions. So I want to just talk about aspects of like how this works and just build it up. And again, please ask lots of questions. Okay, so if you look at the drone, it's got the main 4K camera on a 3-axis gimbal, and that's kind of what we were looking at here. And then it has 6 navigation cameras, so you can look at the geometry of the drone. There's 3 on top and 3 on the bottom. And they're actually these crazy super fisheye cameras, so they see 200 degrees, so they see like beyond the hemisphere, which means the 3 on the top can basically see the upper hemisphere in trinocular view, and then the 3 on the bottom can see the bottom hemisphere in trinocular view. And the goal is to get like 360 coverage, so we can do 360, obstacle avoidance and awareness of the scene. So this is what one of the cameras looks like on the bottom and one on the top. The other 4 are pretty similar to these 2. So you can see the view is pretty funky. Like this is one of the propellers. That's the battery on the top that you're seeing from the bottom right side, where this is forward. And then this fin is actually, if you get the drone, you can see it's got this little, by the camera, it's got this fin which protects the camera lens if you were to like drop it down. And it looks a lot bigger here than on the drone itself, but that's because it's just really right next to the camera. And then this is the other, let's see, yeah, I think the other arm is over there that you're seeing from one of the top cameras. So obviously it's this kind of tiny planet distorted view, but this is what we work with, and the cameras are rolling shutter. So doing computer vision on rolling shutter cameras is a really hard problem, because basically what that means is every row is taken at a different time, which means if you're undergoing fast rotation especially, but even fast motion, the contents of the image are as if time is changing in them. So to account for that correctly, you have to be very careful. So here's what it kind of looks like with the navigation cameras put together to create a 360 view. So if you see the clip we were watching before is on the top left, but that is of the full sort of sphere where you can see, it's just this yellow outline. Does that make sense? So the navigation cameras give a lot more context, and that's what we use for all the algorithms. So the core things we basically need to do to make this drone fly are: 1, state estimation. So we need to estimate our trajectory, how we're moving in the world, and the second thing is obstacle avoidance, like building a dense map of the environment in a way that we can use to navigate. The third thing is detection and tracking of objects. So in this case, the biker, seeing them in the image, estimating them in 3D, predicting their trajectory. And the fourth thing is motion planning. So with that sort of understanding of the scene, we want to figure out what is the best flight path that sort of, in this case, provides really cinematic video and is also not crashing, is also smooth, and respects the physical dynamics of the vehicle, like being able to push the limits of aggressiveness, but if you need it, but without sort of commanding something that is not possible by the physical vehicle. Okay, and then here is the same 360 view with a depth estimate at the bottom. So this is one way of visualizing the full output of our depth estimation system, where the close pixels are more yellow. And so you can imagine how that is really useful for obstacle avoidance, because you can directly kind of feed into the planning system as a 3D map. I'm visualizing it here in this, we call this an equirectangular view because it's a nice way to show the 360. But this is not actually how we use the system online. Okay, and then here's one more way of viewing like a single instance in time. Here it's a point cloud view that is kind of colored by the pixels themselves. This guy up here, that's the drone. That's the trajectory the drone was flying, and then here's the person's trajectory. Does that make sense? And then we have, the scene around us, and then it's going to switch to a depth view. So instead of being colored by the pixels themselves, they'll be colored by the range from the vehicle. So the distance of each point from the vehicle, similar to what we were looking at before, but now in 3D. Okay. Cool. So I'm going to talk a little bit about what we need to do in terms of state estimation. And this was actually our first drone, the R1, that it's a picture of. But anything that is, could potentially be variable on the drone, we want to model and estimate. So the obvious one is the trajectory of the robot, which would be like a pose in space. So a position, velocity, orientation, angular velocity over time of the robot. And we do this with our visual inertial odometry system. I'll show one slide after this. We also have several IMUs, and so accelerometer gyroscope, which is super useful for propagating short-term data. It really only works to integrate the IMU for a matter of, or at least the accelerometer for maybe a second. Beyond that, on a drone and with the sort of size and cost constraints, it is too noisy. But IMUs have biases, and estimating them correctly is key to being able to effectively use them. And then we have the poses of the cameras on the vehicle. So we obviously have CAD of the lenses, and they get calibrated at factory time. And we take that and we put that into our model of how we're going to go from things in the image in 2D to 3D. And the problem is those move around, so every vehicle is a little bit different just because of the physical characteristics. So they get calibrated in the factory by a robot that waves them around a bunch of tags, and we know how to model that. We have a model for the camera lenses, and we calibrate that, and also their poses. The problem with that is that they also move around when, as the vehicle undergoes temperature changes especially. So it's a magnesium frame with plastic pieces, and those things expand and contract. And any small amount of rotation, like even a small fraction of a degree, significantly changes the actual results you get when something is 20 meters away. So the problem is that the ability of estimating depth or really doing odometry from things at distance, it depends on the inverse range of the object you're looking at. And so as you get that far out, you're really looking for fractional differences between, fractional differences of a pixel between multiple images. And that makes you, that makes it so that you have to be very careful about your calibration. So we calibrate the poses of the cameras, and particularly it's mostly about the rotation. Like the actual translation of the cameras moving, it does not have a large effect on the results. It's mostly rotations. But we calibrate those things online, sort of jointly with our odometry system. So there are many variables in the optimization, some of which are the the pose of the robot, but also the poses of the cameras and the biases of the IMU. And additionally, we calibrate the intrinsic parameters of our lenses, which is kind of nuts thing to do online, but those also change. I'll show a video of that here. So this is showing a temperature sweep of a fixed lens, and you can actually see sort of, these circles are fixed, but you can see how much it moves. There's actually several pixels of motion there over the change, and those are the intrinsic lens parameters, the distortion model of the camera. And so to really handle this, we also estimate these online with everything else, which is a cool and a hard problem. And then, of course, we have the propeller spinning, so we want to estimate the rates of those propellers. And then we have the gimbal, and we estimate a combination of ways exactly where the user camera is pointed, because while we have sensors on the gimbal that tell us where we think it is, and we've commanded it to be somewhere, it's also on an isolation system, and there are other changes there. So we also additionally do visual estimation of between the user camera and the navigation cameras to line those things up. Cool. So here's just a quick visualization of the visual inertial odometry system. So on the bottom left are some features that are being tracked. In this case, they're sparse features, just tracked over time in one camera. And on the right is the estimated trajectory of the robot. So I think you guys have gone through kind of a traditional SLAM pipeline. Is that right in this class? Sort of, maybe. Okay, well, anyway, so what you get is a bunch of 2D observations in your camera images by tracking in your images, and you can track either between cameras at a single time instant, or you can track over time, and really you want to kind of do both, and there's different characteristics of what works well, but then you take that and you are jointly optimizing for a 3D locations of those landmarks that agree with the observations you've made in the images, while also solving for your own pose. And the residual in this kind of objective will be the reprojection of that 3D point into your camera model for your pose, and those are all variables in your optimization, result in a pixel coordinate, and then you would compare that pixel coordinate to the pixel coordinate at which you actually observed that feature in that camera. And with multiple observations of what you think is the same 3D point, that starts to constrain things in this system. Okay. Still no? Okay. So here's a little bit of what rolling shutter can look like. In this case, it's rolling shutter combined with vibration. It's slowed down a lot. It's a little subtle to see here, but you can see these like wiggles. We call it wibble wobble. So the car, you can see the windshield of the car sort of waving around, and that if you're not modeling that, if you're not accounting for it, that's just pure noise that's going to mess things up for you in a way that does not match geometric constraints. The way if this is happening to you, you have two choices. Choice one is to improve your hardware, improve your system such that you don't get this issue. Like there might be a certain, say, frequency of vibration that is related to the time it takes to read out in your camera, and you get some periodic signal. Option two is to have a way of estimating exactly how the camera moved during this time period and accounting for that, which requires very careful work. And we do both of these things. But it's once you're trying to fly at high speeds in aggressive scenarios, you really have to be pushing the edge of what we can model there and what we can estimate. Okay, cool. This is one of my favorite slides because I think it talks about what is really hard about computer vision, at least computer vision in a production robot. So A here is just thin branches. So flying in a forest, right now it's in winter, we're going to have a bunch of customers. They're going to take their drones and they're going to try to follow themselves riding a bike in the forest, and there's going to be all kinds of terrifying thin branches that you can barely see. And we work really, really hard on being able to see that from the cameras. I'll make the bold claim that I think we're almost definitely the best in the world at seeing really fine, thin cameras from, or thin branches from camera images. And when you're flying at, you kind of have to think about, like, what's the resolution of my camera? How fast am I flying? What's my physical reaction time to either steer away or stop? It's obviously not guaranteed you have a way to steer away. So you could really be thinking about, okay, if I'm flying at 35 miles per hour, and there's how far away do I have to see an object to be able to stop if it suddenly pops in? And that kind of plays into how faint does it, what is the smallest perceptible signal you can have in your camera images before you have a chance of seeing that. And I think we're pretty close to the limit there of, if you can, as a human, look at the camera image and see something, we probably see it as well. But it's still we're up against that edge of just how much signal can we get out of that. So B here is a really fun scenario where there's a bright sun, so the tough lighting conditions make everything harder, right? So in this case, there's a low sun, and we're in a forest, and the particular problem here, these are actually images from R1, the first drone, but it's very similar. So the slide on the left, the camera on the left is, I think, has a smudge on it, like a fingerprint on the lens, which basically makes just light goes differently into the camera, and the left and right cameras look very different there. What that means is that if you're looking between the images for a photometric signal, they're not agreeing at all. So typically what you might do for a stereo vision algorithm is look at two cameras and look along an epipolar line and look for something where say a small patch of pixels looks the same in the left and right camera. The problem is if you're up over here you just got these crazy vertical sun rays that will match other sun rays in a totally inconsistent way, but not your actual contents. So it's a huge source of noise. And especially when it's different between the two cameras. And then C is just motion blur, so the drone can, that's kind of our decision unless it hits something and flips over, but to allow very aggressive rotations up to several hundred degrees per second, which induces motion blur in the cameras. D is just reflections and mirrors. I really don't have a good solution for that. If you fly this drone in front of a panel of glass that's 3 meters by 3 meters wide, it will see what's inside and think it can fly in. The hope of doing this semantically is it's tough. It's really tough. And then mirrors, of course, in this case, a reflective building. So what we typically hope is that these vertical struts, we're able, those make geometric sense and would prevent us from flying into it. But the part of the mirror that's just reflecting the building behind, well, that just looks like an opposite world that's geometrically consistent. And so our depth map will reflect that it thinks that these are basically poles, and then there's something behind there. If you look closely, you can kind of see there's some blinds in here, so horizontally. And so at some point of if you can see what's in the window and you can see what's behind, you have to there's two potential realities for what that could be. And it's an interesting problem to think about when that switch would happen and which taking the stronger signal. Okay, so E is just big textureless surfaces. So let's say the drone's right up against the ceiling, is typically the hardest of cases, and really only sees what E looks like, so it's just white. And that's also what the sky looks like in a lot of scenarios. Now, sometimes the sky is bright blue, but not always. Often it's just basically saturated whiteness from the cameras. And deciding which of those two is the case is a really hard problem. The best thing that can help you there is like the fact that we have full 360 context on the drone means that the rest of the scene can tell us, oh, is this more likely to be an indoor scene with a room, or is this going to be, we're flying out in an outdoor scene. And the reason it matters so much is because, well, the sky is one of the best directions to fly in. Like it's usually very safe. And so if we're trying to get away from something and try to figure out how to move, like going up is usually a very good decision, but not if it's a ceiling. Then you're going to have a bad time. Okay, and then F is water. So there's just water droplets on the lens. I mentioned smudges from your fingerprint, also dirt, also dust, also cracked lenses, just all manner of things that inhibit the sensor. And this is something that we don't particularly control, right? The user is responsible. They get for cleaning the lenses, but they take this drone somewhere that we've never been, and we ask them to wipe the thing, and we detect these things online. Like that's the best thing we can do. So actually, as the drone is flying, we look for potential issues with what the cameras see and having dirty lenses, and we have sort of we have a lot of these types of warnings, but this is an interesting one in particular. Is like we have multiple levels of like, oh, it looks like your lenses are dirty. Like you should probably land and clean them and try again, and you can dismiss that, and most people just dismiss it and don't listen. And then there's another level that's like, okay, you really have dirty cameras, like we're not gonna let you say track anymore, so the drone just kind of like goes into a hover, and it's like, oh, it's not safe. But we can't just make the drone land or something, because the drone could be a couple kilometers out over the ocean or something, and just hovering there or landing is not a good acceptable solution, and just coming back on its own is also dangerous. So what we sort of chose to do there is for the drone to just hover, and you can control it manually on your phone or with a controller, but it won't like track you, because then it's sort of more autonomous and you're oblivious to the fact that its performance is degraded for sure. So we care about lots of those types of robustness issues, because it's just like getting to a demo that works of like, okay, we have this drone, it films somebody, it avoids obstacles, like that is just much easier obviously than getting to the point where you can actually have something where someone paid for a product and they take it somewhere new and they like initially don't trust it, but what we typically see is after like 1 or 2 flights of no problems, it works, and in the vast majority of scenes, you're not going to have any issue, but you quickly just gain way too much confidence in the robot just to work anywhere, anytime, and that's something that we kind of struggle with, is how to like communicate limitations in an effective way, because it does work so well in so many cases. Okay, talk a little bit about mapping. So, and by talk I mean show this video. So these are just, like a voxel representation over the user camera video, basically just to look cool. So in terms of dense mapping, so the goals from state estimation are different, right? Because for estimating how we're moving, basically we have cameras in every direction, and you don't need a lot of points. Like you need a little bit of information about how other things are moving that are static, and you track them well. Which means if something is very difficult, like a crazy tangle of thin branches, you can just ignore that part and look at the ground or look at the tops of the trees, and that's enough to tell you how you're moving. But for actually mapping things, like we need to pay attention to every single direction and make a decision about that, saying, oh, this direction's like too hard to look at. Like you can decide to never fly in that direction, but that's very limiting. So we published one paper here a couple of years ago with a research intern named Alex Kendall, and the paper was basically trying to combine a classical stereo matching pipeline, like geometric reasoning about stereo vision with deep learning to learn features and do the matching. So at the time, we did really well on these, the Kitty self-driving data set, which we submitted to. And basically the bottom one here is the ground truth of that data set, which is a LiDAR scan. And then the middle is a prediction of our network. And so it worked really well in these scenes. I'm not going to go into details here, but essentially the network was structured in a way to take advantage of sort of intuition about stereo matching and classical stereo matching algorithms, where we compute shared learned weights on each of the two images with two towers, and then we have a cost volume approach where we kind of mix those features together at different possible disparities, and then we regularize the cost volume with 3D convolutions, and then we pick a winner. So this worked really well, but I'll kind of give a couple of caveats. The first caveat is it ran at 1 frame per second on a Titan X GPU, which meant like obviously we can't use it. It's orders of magnitude off. And the second caveat is that frankly, the Kitty data set, or really like in my experience, any self-driving data set that I've seen are incredibly easy compared to the types of scenes that drones tend to see in the wild. And the reason is because of regularity. So most of the images just look very similar. Like you have a road scene, you have cars, there's always a ground plane, there's things on the sides, there are street signs that are vertical, and there's just a ton of semantic priors you can do. This is why monocular depth estimation works really well on driving scenes as well, when things are, when things are normal. Now that's not always the case, but for a drone, you can be flying really in any nook or cranny of any building or wild, and you really can't tell what's in a lot of the camera images, and there's no good monocular prior a lot of the time because you could just be inside some random geometric shape in a sculpture, in an art gallery or something, and so it's a much harder problem for that. And specifically the metrics on a data set like Kitty, where you're typically measured on like how accurate is like the average pixel error across the image, right? Like I can't emphasize enough just how useless that is for robotic navigation purposes. Like being 1% closer, like it's basically just dominated by how well do you estimate the ground plane and the exact pixel values of the depths. And if you have something like a thin object that you miss, or an entire vehicle, but it's further away or something, like it has very little to no impact on the score. And so focusing on metrics that really matter for autonomous navigation, were things like 3D occupancy and just thinking about only the parts of the scene that matter. And in the end, like in the Berkeley way, kind of one of the most powerful ways to do that is to think about the sort of action space, like what are the parts of the scene that actually matter for making a decision, rather than allocating your error metric by pixel values, which is totally simple to think about, but pretty meaningless. Okay, so since then, we've made it a lot faster and a lot better, and it's also changed in many, many ways, but basically we are flying deep networks that produce depths and build an obstacle map for us, and it runs at approximately 1,000 times faster than the previous sort of first thing that I mentioned. And actually think we were the first ones to fly a robot based in a complex scene based on sort of a deep learned obstacle avoidance system about a year and a half ago. This was our little ATV flight. Yeah. Yeah, it's a good question. Basically, we do a bit of both. Like we aggregate the images, but the dominant part of the deep learning estimation right now is between the sort of the cameras at an instant in time. but we definitely do things that are between, like temporally as well. There are different challenges into doing that. One of the challenges is moving objects. Moving objects, you have to estimate that motion to geometrically get the correct thing, right? Like if you're doing optical flow, and then you assume things are static, you'll get incorrect depths. In particular, like if you're flying the same speed as somebody and following a biker, say, and they and you do that and you think they're static, like it'll seem like they're far away because basically they don't move with respect to you, and so the pixels, you stay in the same pixel location, which means which implies that they're basically at infinity. So there's tricky things like that to take into account. Yeah, I'm going to show a couple of just clips of the sort of hard things we focus on. So this is just a forest with a bunch of branches, and looking, like, really what you care about here is, like, did you see this object or not? And generally the, like, 3D extent of it, but the exact details of the shape really don't matter very much, although it does tend to be correlated with, the quality of your predictions. Here's a 3D view of that same thing where we have the camera image on the bottom left and then the depth on the bottom right. Okay, power lines are real and something to be worried about. So, okay, here you can see, it's a little hard to tell here. Oh, these aren't matching, are they? That's annoying. Okay, well, so you can kind of see, if you trace this out, there are a bunch of power lines in this image. So these ones obviously are very clear. You can see this is a faint, but you can see it. Over here it kind of fades into the background. This is a power line that's quite faint to see, and it disappears entirely behind the sun here. And then actually up here there's one that goes all the way across like that. And it's very, very hard to see. So I'm just giving some intuition for that, and then there's a second one here, and there's a third one here, and so it really, like, it does depend a lot on the background and the lighting on everything, just when it gets into your camera image and how much that works. So again, that's kind of the walls we tend to be up against, trying to push the limits of where we can fly, what we can see, and how fast we can go, especially. And then about textureless surfaces, so here's actually flying through our office, and you can see on the left here, for example, it's a scene with specularities on the walls, which will be lying to you photometrically, and just a lot of white texture. And then here is the same thing in 3D. It's funny, this blue glow on the bottom is actually because there are some different lights on the drone, but in this case, this LED was on, which is very close to this camera, and it basically just shines this blue halo under right there on the ground. But we don't keep this one on in flight. Normally, it's just these guys, which have been designed to not be seen by the cameras. And the whole kind of, I should mention, the whole geometry of the drone and the inversion and everything is kind of built around enabling as much visibility as possible of the world without obstructions. Yeah?
What's the onboard update depth estimation frequency?
The frequency? So I can't say exactly what frequency is. Part of the reason is because it's sort of internal stuff, and part of the reason is because it can change based on some different things. So we are pretty clever about some of the things we do in terms of, what resolution do you process stuff at? How complicated of algorithms do you run, or intensive? And which directions do you focus on? So all those things in terms of like downsampling and foveation and choosing the the extent of the algorithm you run are pretty important to finding the best balance. And so, for example, if you're flying really fast such that it's really dynamically infeasible for you to even move in these other directions, for the purpose of navigation, it doesn't really make sense to focus your efforts there. You really want to kind of like pick the cone and just do tunnel vision there. Now, the kind of, in a different case, like for example, let's say you're barreling down this way at max speed, but you're also filming something that's over there. Now you may want to focus on those two directions instead of just the one, because you need to estimate the scene over there to make some decisions about your high-level objectives and then obstacle avoidance over here. So things like that are important games to play. Okay, here's another fun one that's just artistic. This is just an example of someone basically pushing back on the joysticks. So we have a bunch of accessories, but one is just it's a controller, and you can fly. And the idea is basically like you control a drone like normal, kind of if you've ever flown these Mode 2 joysticks. And the idea is that you don't have to be an expert pilot. Like you can just push it forward and it won't crash, right? It'll go around things. It will do its thing. So it's a really fun way to fly because it means you can either just have fun or do your task, film something, but you're not worried about the physics of the drone or it crashing or things like that. And that's what this shot was, basically just pushing back on the sticks. Okay. So this is, can't tell if you guys can see this at all, but this is kind of a typical example of what a thin branch looks like in an image. So these are actually two images. It's quite a close branch. So you have a sense of like, here's the branch, and then here's the branch. So if you look closely, it's coming out of the ground over here, and then it comes all the way down very close to the camera. And so the actual correct sort of match of this stick is moving from here to here. And then there's another one over here that's moving like that. So if you look closely, you can kind of get a sense of that. And so this is just, I don't know, maybe conveying a sense of the type of problem here, which is one of the hardest things we need to do, which is just carefully pick out objects. And there's kind of the outline in this image of what we're looking at. And actually, a real key here is like if you flip between two images, you can tell. But if you're just looking at a single image, you can't. Like no human can, and really no algorithm can either. Like you can look at this kind of scene all day, a tangle of branches, and not have any idea what the closest thing in there is, which really shows that's kind of what I was getting at, the difference between a road type scene, which is very regular, and this type of scene. Here's another fun one where we're actually above power lines. So there's one power line here you can see that's moving. There's another, I think, really faint one here. And then there's two right here that you can see very clearly on this part and then disappear mostly up in that section. Okay. Let's mention, so we have, we can play with simulated data, synthetic data, and the cool thing about that is, we know everything about it, and we can try to make it realistic. We also have real data, and the problem with real data is we don't have any ground truth for the depth, which is a very tough problem. And there's a whole body of research that focuses on trying to learn from unsupervised data, which is really interesting. The problem is that slide I showed about all the things that make vision hard. None of those things are photometrically consistent. So if that's your cue to learn depth, that's not a solved problem right now because that cue won't get you the really hard things. So here's kind of a fun example of something where we took suns, like synthetic suns that we generated, and we just put them in real images. And the kind of fun thing you can do there is say, oh, well, whatever you predicted before the sun was there, you should predict the same thing with the sun. So that's kind of one way of getting at without knowing everything, at least gaining some robustness to a really big, bright sun. Okay, let me show a little bit about tracking and detection. So this is kind of a fun video of just tracking somebody through a forest with a bunch of lighting changes and occlusions and pose change. So people change shape a lot. And we're reprojecting the 3D trajectory into the image, which you need a pretty accurate estimate of the robot's trajectory to do. And then on the top right is actual output of a deep network that predicts the pixels of this person instance at that time step. And on the bottom right is just the top-down view of where the drone was and where the person was. And then the red vector is just an estimate of the velocity. So like what's in a linear sense, where's that person going to go in the next little bit. Cool. So the way we do this is kind of the way we do everything else, which is a combination of geometric reasoning and deep learning for semantics in the images to be combined with like 3D motion and things we know tend to be true about the world. So, oh yeah, so multi-object tracking is, even if you're just tracking one person, which is more common, tracking multiple objects is really useful because you can then discriminate between people rather than just saying everyone else's background. You can say, oh, this person A disappeared, but person B matches person B from before, rather than person B also just appeared and which one's the right person. So these are our three co-founders just running among each other, and we're doing a pretty good job of keeping him in frame, or keeping him as the correct estimate. And then on the bottom, oh boy. Okay, on the bottom right here is kind of a fun failure mode where, it's hard to see, but so Abbeel run behind Matt here, and then, or Adam, and Matt pops out at the same instant. So like there's one person goes behind and hides, and the other person that was hiding pops out, and they're kind of at a similar velocity. And so the things you're combining are like, where are they, their positions, their velocities. Someone's unlikely to just suddenly stop, but it can happen. And then their like estimate, the visual estimate of their body's appearance, which we do with deep networks. And so in this case, the visual estimate is similar enough that like the chance of one person disappearing and another appearing and then being at the same velocity is like very low. And it clearly is, yeah.
What features do you use to distinguish between the different people?
They're basically learned features. So essentially it's based on the appearance of an instance of an object. And there's pretty solid body of literature about how to try to learn those things, but you tend to have learn through examples of people that look, there's different constraints based on what type of like use you want to do, but typically it's like you have similar instances, you have the same instance of a person, but from many different views and poses and lighting and all that, and then you have multiple people that look similar, and you train positive and negative examples, and you learn that kind of task. This is very common for like, I guess like surveillance camera data sets. They tend to be easy to collect where they're just fixed. Now again, the drone is a lot harder because it's moving, and people tend to be moving very quickly and running away and doing flips and stuff, which make the problem a lot harder. But the concept is pretty similar. Yeah.
How do you tell the drone which object they should start tracking to begin with?
Oh yeah. So just for the sort of consumer follow use case, basically you just take off, and then whatever is in the view of the user camera, you'll see just icons on the phone. So we do people in cars, and so you'll just see a little plus icon, and then you just tap, and then it works, and it shows that halo that was in the launch video earlier on the phone. We also have this thing called the beacon. It's another accessory. So this guy is just a little puck that lets you basically fly without your phone, and it has a GPS that we trust a lot more. And so what this does is, if it lets the drone, if it loses visual tracking, if you get stuck or something fails, it can basically try to just combine between that and the GPS estimate, and then find you again and pick you up visually. And so the idea is just to make it much more robust in terms of if you're skiing or something that you're just hands, you don't have to worry about it. And so the other way we do it, which is kind of fun, is if you take off like this, it will take off, and if there was someone standing right there, it will just track that person. Okay, cool. Say a little bit about planning. So I think generally we have a bunch of knowledge of the environment. It's all uncertain. There's no guarantees about anything because we're not sure if we saw the thin branch. We think we know where we are. There's uncertainty about all these things. We try to reason about that in the best way possible. In the end, we have some measurements, and we need a policy that decides what the propeller should do, such that the drone accomplishes our goals. Some of which are down here, like obstacle avoidance, dynamic limits, smoothness, effective tracking, and cinematic quality of the video. And these are all, there are hard trade-offs with each other. It's not easy to achieve these things in all but the simplest of cases. So I think it breaks down in a way that I think you've all kind of seen before. So I won't go into this one, but basically, we have the most interesting part of the problem is figuring out what the cost function should be based on everything we know. And so based on the current state of things and the full environment, what are the actions we should choose that give us the best result? And defining that function is a lot of work and trial and error and investigation. And that's something we just work a ton on, just iteratively, trying things out, flying it, seeing what fails, trying to figure out what are discrepancies between what we really want and what we saw, which is a really fun problem. And then you actually need to find an action that accomplishes that goal. And that's the cycle. And then either you didn't have the right objective, or you didn't find the minimum for that objective well enough to do what you wanted. And in terms of solving it, I think you guys all know, but you can learn. That's the promise of deep reinforcement learning, is that you can potentially learn both of these things from data, and you can do sampling techniques, you can do trajectory library, you can do a tree-based search, or you can do optimization. You can do trajectory optimization, model predictive control to solve these things. And so we basically do a combination of all these things in a way. But what is cool is we run something on board that runs at 500 iterations per second that is reasoning about kind of the whole stack between all the way up to obstacle avoidance and cinematic quality, all down to what are the dynamic limits on the rotors. And the more you can reason about the whole system together rather than in separate little layers that have their own boundaries, the more you can get out of the robot. And I think that's kind of universally true. The trick is that you have to be a lot more careful. It's a more dangerous game to play. And again, we also use sampling techniques, and they have a good role to play within the system. Then I'll just add a note about simulation, because it's awesome and super useful, especially for motion planning. There's for computer vision, you want these really photorealistic images that you've carefully curated. For planning, you don't care. You just need something that is good enough to see your behaviors and try things out on. So this is we literally drive this guy around with a joystick at our computers, and he just kind of slides around the world, and we just use that to test basic things. And then even without images, we have these scenes where basically we generate a random forest, and we want to say compare. We want to figure out, okay, how far away from obstacles should the drone stay to not crash into them, versus how often is it going to get stuck in a dense forest if we do that. So we can we tend to run logs against hundreds and thousands of regressions against a ton of just recorded log data, right? So we record all of our flights, all of the images, and we can rerun all our vision algorithms and check like those types of things. But for planning, you can't change what the robot did, right? It's all kind of off policy, and so simulation is really helpful there. And so we can run an experiment like, generate a bunch of different random forests and have the subject run the same path through them and then see how often the drone hits something or gets stuck and have a statistical sense of what to do there. The problem is always like something bad happens, we look at that log and then we're like, okay, we can tweak this thing to fix it, but then did we just make 5 other things worse? And we can't do 1,000 real flights to test that in any sane way. So maintaining the sort of infrastructure to handle all those things is really critical. Yeah?
Is the drone currently able to localize itself indoors and fly to a fixed point that you want? Say like you want the drone to fly X years forward, is it able to do that?
Yeah. Yeah. I mentioned I would fly in here, but I don't think I'm allowed to. Yeah?
Do you learn the dynamics model?
So that's a good question. We identify the dynamics model, which is somewhere between them, but we definitely model the dynamics of this drone. It's not like a model-free black box. And the reason because it's eminently modelable. So it is, the propellers, there are aerodynamic effects that we understand quite well. There's the inertias of the drone and the properties of it. And so we model everything that we can, and we try to fit parameters to it based on flight data. And then I think that's pretty different from other types of robots that are more like, especially when you're dealing with contacts and more complicated things. But this is not that many degrees of freedom there. I think the complicated part comes from aerodynamics. So once you're flying fast and you're in turbulent flow and you get these types of like pitching moments and the accelerations of your rotors play into things. And so there is a lot of complexity there, but it's also complexity that has been pretty well modeled in aerospace, at least in terms of the structure of something that you can learn. So, yeah. Yeah?
On the last slide, you said you have a nonlinear MPC running.
Uh-huh.
How do you ensure that you reach a feasible solution?
We don't. I mean, you can't ensure anything because, well, I guess it's a complicated question. That's not exactly, but sometimes people ask like, how do you guarantee that it's going to be obstacle free, for example? And the answer to that is we can't because of perception. And so nothing is ever guaranteed, but we do our best. So in terms of like, if you have a nonlinear MPC, how do you make sure that it converges? Well, it depends a lot on how you're solving it. There are good ways to know if you've made it worse than your initial guess, for example. So if you do that, you can try to fall back to something else, or you just like try to work towards robustness. So have ways of just managing what you're doing such that you at least have some path that moves you forward and is not catastrophic. But I think the best way to do that is just to try to carefully design your problem, your constraints, and the setup of what you have to have stability and convergence. And there's a ton of work that could be put into that is tricky. But there's no fallback that's a good fallback, because let's say a fallback is like go constant velocity. Well, you might just run into something, or like, yeah, but you could, for example, say, oh, I'm going to stop caring about any of my other high-level stuff, and I just want to like come to a stop with obstacle avoidance if it's a really bad scenario. Yeah. Okay. Just another video of simulation. And the kind of cool thing about simulation, so this is actually from an SDK that we have. It's kind of in a private beta SDK where we let people work on it that we think make a lot of sense to kind of develop on our drone. But the cool thing is to share that simulation between like our purposes and actually being able to turn the drone into something that you can program. So at a high level, like make it move around, make it do things, but not have to care about obstacle avoidance. and again, the low-level stuff. So it's a hard problem because controlling a drone, like, you have to understand a lot of the internals of the system to do it. So we're kind of always thinking about what is the way to try to design an API such that it's intuitive for people to understand, especially people that aren't experienced with drones or even robotics, to be able to control things and get what they want and sort of understand the why it might not be able to do something and why it might be able to do something else. Okay, cool. Let me just show a couple of other cool things. So we estimate the wind online, which is really useful to have as a model to do more effective planning and aerodynamic control of the drone. This is something neat. It's a lot less relevant for this drone, but the first drone had perimeter guards. And the reason it had perimeter guards is to have cameras that can see, like, on the outside. That's why we very carefully designed the geometry of this drone to try to get rid of the perimeter guards, because they're so expensive and bulky and bad for performance while still having visibility. But the cool thing was it could bump into things and not have the propellers touch it. And in this case, like, we fly into this glass intentionally, and we actually detect that collision and we add that obstacle into our map there. So we won't do it again, which is a pretty neat thing to do. And then, yeah, we look a lot at sort of recovery from dynamic maneuvers. So we call this the inverted pizza toss, where your initial condition is like upside down and then spinning quickly, and then the drone kind of has to come down and recover. This is another fun one where there's prior work on this as like its own controller, but something neat that we found was that if you actually, basically just with parameter changes to our planning system, if we shut off one rotor, we find this kind of mode of flight where it's still semi-stable, where you're not controlling yaw anymore, but you're able to sort of hover and come down to a land. This is all in simulation, at least so far, because the question of state estimation in this scenario is a lot harder. But it's pretty cool that, like, by just spinning really fast, you're able to stay hovering with 3 rotors. And in fact, what we did was show that we can, again in simulation, actually follow somebody and avoid obstacles while just having 3 propellers and spinning like a madman. So I don't think anyone's shown that before. Okay. These are slides from CVPR. It's a vision conference, so I'm going to skip those, other than to say that, in fact, I already talked about, yeah, don't work on deep learning benchmarks and try to improve them by 1%. That's a sucky thing to do. Work on hard things and real robots. And that's, I think, what this class is all about, so that's awesome. Okay, and then I'm just going to show one last video, which is one of my favorites. Just 4 drones following Jack here as he goes down a water slide, just in every direction. And it's just a fun thing to watch. All right, cool. Yeah, so we get a lot of sweet videos, and again, so our goal is to, like, bring these drones to doing useful things, not just for video capture, for, you know, content for consumers in action sports, but also for inspection and mapping and construction and all these places where you need a trustworthy, reliable robot that can move around anywhere and get and sense things, basically. All right, that's it. Yeah. Thank you. Cool. And then, yeah, if any of you guys are, like, looking at internships, or I know a lot of you are graduate students, so I'd be happy to hear from basically anybody in this class. We have, you know, we have a jobs page on our website, or my email is just Hayk, Hayk @Skydio. I'd love to hear from any of you. Yeah, thanks for coming.